Example 4. A manufacturer wants to design an open box having a square base. Well, this will sort of work. Let's talk about that cap later in the year. An open box having a square base with a surface area of 156 square centimeters. What dimensions will produce a box with maximum volume? Okay, so a square base. What dimensions will produce a box with maximum volume? So I need to maximize volume. If the base is square, then what do I know about these two sides? They're equal. I don't know what they are, but whatever they are the same. So x and x. I don't know how tall my box is. But we'll just call that y. And it's an open box, so no top. So that matters with the surface area. So the surface area is 156. The volume is length times width times height. Which one of those is the primary equation? Which one am I going to be taking a derivative of? The volume, because that's what I want to maximize. Which means my surface area is supposed to be a secondary or a helper equation. So I need to come up with the surface area in terms of x's and y's. Well, this is one where you're not going to get a formula. You're just going to have to look at the picture. What's the surface area of the base? X squared. What's the surface area of one of these sides? XY. And how many sides are there? Yeah, 4 of them. So there's 4 XYs. There's 1 X squared because it's an open box. If it was a closed box, then we'd have 2x squared. Well, I don't think there's much of a choice here. Would you like to solve for x or for y in the secondary equation? I mean, neither one of them's nice, but one's a whole lot better than the other. You gotta solve for y. To solve for x, you could do it, you'd have to use the quadratic formula and you'd have a mess on your hands. So let's solve for y. So 4xy equals 156 minus x squared. And then we'll divide everybody by 4x. I think this is going to be easier if I split this up. Because I can reduce different pieces of it. I think that's going to be a little bit easier. We'll see. 156 over 4. Old school, elementary school division here. 39. 39 over x minus x over 4. Okay, not the prettiest thing, but way better than trying to solve for x. And if we had solved for x, we'd have to square it, so that would have been yuck. So definitely the right choice to solve for y. So our volume is x squared times y, but y is 39 over x minus x over 4. Again, the goal is to take the derivative of volume, set it equal to 0, see what's a max or a min, but I got to get it to one variable. And this actually worked out. I was worried about that x in the denominator because that was going to be a pain for a derivative, but never mind. It worked out just fine. 39x over x minus x cubed over 4. Okay, what next? Do I want to set that equal to 0? I want to take the derivative and set the derivative equal to 0. By the way, this is not a parabola. Negative x cubed, so I don't know, looks something like that. And we're trying to find maximum. So we want that, although it looks like there might be a minimum in there somewhere too, so we have to be careful. Make sure we grab the maximum. Alright, so v prime is 39 minus 3x squared over 4. So, let's see. Set it equal to 0. So 3x squared over 4 equals 39. Times 4/3. Well, it's ugly, but it's not as ugly as it could have been, because the 39 and the 3 reduce to 13. 13 times 4 is 52. So x equals square root of 52. Sort of technically plus or minus, but why am I pausing? What's the but? It's not a negative. Like this is a box. I can't have a box that's a negative, so I can throw that one out. And I also wonder now if that negative square root 52 was where a minimum was, like sort of mathematically, even though physically that would not be possible. So x is the square root of 52. In fact, I am going to go with this because there's two critical points. We found them both. The bigger one has to be the maximum, and that's the only one we have left. So if we really wanted to prove it, we'd have to do the sign chart with v prime, but I'm convinced that we found it because I know what the graph of an x cubed looks like, at least a negative x cubed anyway. Alright, now we got to go back and make sure we answer the right question. What dimensions? Okay, so I've got x. I just need y. But I've got a formula for y. So 39 over square root 52 minus square root 52 over 4. Does that reduce? The proper answer is we don't care, right? I don't know. Square root of 52 has a 4 in there, so yeah, it could reduce, but we're not worried about that. So, especially with a picture, we now know that it's x by y, and we've given x and y. Questions on that one? Yes, sir.
Why do we not do the chain rule with the fraction?
So where are we? Back right in here. With the fraction.
Yeah.
So that's just a 1/4 sitting out front, and the derivative of x cubed is 3x squared.
So we could just.
And that 1/4, or the negative 1/4, is just a constant multiplier out front.
Okay.
Did you mean quotient rule? You said chain rule.
Yeah. Quotient rule.
If you had done quotient rule, it works out.
Oh, does it?
Because the derivative, what's the derivative of 4? 0. So yes, if you forget and you try to do the quotient rule on this, which is fairly common among students who are still figuring out when to use what, it'll be ugly, but it'll still work out because the derivative 4 is 0, and so it'll wipe out a lot of what you're doing. Number 5. A cylindrical metal container, open at the top. So again, I'm already thinking surface area. It's got one circle, but not two circles. The cost of material for the bottom is 50 cents per inch squared. The cost of material for the curved side is 25 cents per inch squared. Find the dimensions that will minimize the cost of the material. Okay, so I want volume to be, or volume has to be 54 pi inches cubed. Like if this thing won't hold that much, I mean the whole point of this problem is design a cylinder that'll hold that much water or whatever this is. But the cost, well, there's a cost of the bottom plus the cost of the side. Sides? I guess it's just side, because it's a cylinder. Okay, let's see. I need some dimensions. So what dimensions, find the dimensions. What dimensions would I be looking for? What are the dimensions of a cylinder? The height. And what else? The radius. Okay, so do you know the volume of a cylinder? You would be given its volume, pi r squared h. So pi r squared h equals 54 pi. And now I see why they stuck a pi in there, because at least that part goes away. Maybe we need to back up a second. Big picture. Which one of these equations are we going to take the derivative of? Cost or volume? Cost, because that's what we're trying to optimize. So cost is my primary, volume is my secondary, which makes sense now because it's got both variables in there, equals a number. I'll be able to solve this for something and plug it into the other side. All right, the cost is the bottom plus the cost of the side. Well, the bottom is 50 cents per inch squared, so 0.5 times the area of the bottom. I don't think it's going to give you any formulas for this because this is like a custom shape because there's only one circle involved, pi r squared plus 0.25 times whatever the sort of side area is. It's called the lateral surface area. Let's see, do you know what the shape of that lateral surface area is? If I took apart this cylinder? Yeah, it's a rectangle. So here's my cylinder, but if I unwind it, I get a rectangle. So there's my curved side. I guess it's not curved if I unwind it, but curved side. That's h. That's the height. I guess this is the trick. What about how long that side is? What is it? So like when I do it like this, it's this side. But when I curl it up, what do we call that? Circumference. Which is 2 pi r. So that total area would be 2 pi RH. Alright, so that one, we haven't even done any calculus yet. We've done a lot of geometry. Find the dimensions that minimize the cost, and then find the cost. Right, we want to take the derivative of this, set it equal to 0, and do the optimization on this thing. But before I do that, I need to solve for something over here. You always have a choice. I think there's an obvious choice on this one. You want to solve for h or for r? I would pick h as well. Why not solve for r? Right, because you'd have a square root in there, and then you'd have a really ugly equation over here. It would work. You'd eventually get there. But yeah, let's solve for h. And it's easier on this equation as well, because there's only one spot where h goes in. So my cost is 0.5 pi r squared plus 0.25 times 2 pi r times 54 over r squared. Right, algebra cleanup. Let's see. One of the r's cancels. 2 times 0.25 is 0.5. Half of 54 is 27, and there's still a pi, and one of the r's cancels. Calculus is easy, algebra is hard, right? We still haven't done any calculus on this problem. What do you want to do next? Now we're ready to take a derivative. Now we can see what happens here. So you can call it dc dr, or you could just call it c prime. 2 times 0.5, well that's, it finally did us a favor here. Oh, I don't like 27 pi over r. I'd rather 27 pi r to the negative 1. So minus 27 pi r to the negative 2. A little bit of algebra to the side there. Its derivative would be negative 27 pi r to the negative 2. Set that equal to 0. And I think our calculus is over. Now it's all algebra. Let's see. What do you want to do? How do you want to solve that? Algebra experts.
So pi r on the other side of the equation, and then multiply by r squared on both sides.
Okay. I was going to multiply by r squared first, but that's fine what you said. So pi r equals 27 pi over r squared. Multiply both sides by r squared to get rid of the r squared. Oh, the pi's will cancel, so r cubed equals 27, which is great. Totally a rigged problem that works out that way. R equals 3. This was a mess. I have no idea if that's a max or a min, because I don't know what this... Right? I have no idea what that looks like. So when they're simple and you can sketch it out and know that, okay, here's my critical point, maybe there's another one, but I have no idea what that looks like. So I think I need to do a sign chart with C prime to see what, to make sure this is a, actually I want it to be a minimum, to see if it's a minimum. So C prime of 2 and C prime of 4. Where are we going? Right there. Oh, this is going to be kind of ugly. C prime of 2 would be 2 pi minus 27 pi over 4. It's kind of ugly, but what am I only concerned about? It's negative or positive. What's 2 pi minus 27 pi over 4? It's definitely negative. So that means C is going down. I plug in 4. So I'm looking at C prime, plugging in 4. 4 pi minus 27 pi over 16. Again, not particularly pretty, but 4 minus 27/16 is positive. So that means R equals 3 is a min, which is what we wanted. Okay. What does this question ask? Find the dimensions. Find the dimensions. Got it. R equals 3. Here's one of my answers. My secondary equation usually helps me with my other pieces. So H equals 54 over 3 squared, which you could leave that as an answer, even though 54 divided by 9 is 6. So that's part A. Part B, find the minimum cost. Well, I have a formula for cost somewhere. In fact, I got a lot of formulas for cost. I can pick any of those formulas for cost that I want. This is why it's important to label as you go. C equals, C equals, C equals. I can pick any of those. You got a preference? None of them look great. I think I would just go with the first one, especially since I don't have to simplify anything. 0.5 times pi times 3 squared plus 0.25 times 2 pi times 3 times 6. What does that equal? I have no idea. So if it was a multiple choice test, you might have to simplify that down. Free response, I would leave it at that. Don't risk messing something up. Questions on that one? Number 6. Probably won't have time to finish it, but maybe we can get it set up. An offshore well is located in the ocean at point W, 6 miles from the closest shore point. Alright, so there's my shoreline. Point W is 6 miles away. Maybe I should read the whole problem before starting to draw, because I don't know what else is going on. On a straight shoreline. Okay, well, mine's roughly straight. The oil is to be piped to a shore point B that is 8 miles from point A. It's 8 miles from point A. Oh, shore point B that is 8 miles from point A. By piping it on a straight line underwater from W to some shore point P between A and B. And then on to B via a pipe along the shoreline. Okay, so here's the path of the oil. Picture's so complicated it needs a key to go with it. There's my oil path. The cost of laying pipe is $100,000 per mile underwater. Okay, so W to P is underwater. And that's $100,000 per mile, and 75,000 per mile over land. How far from point A? How far from point A? Okay, this tells me how to label things. How far from point A should point P be located to minimize the cost of laying the pipe? Whew. Made up weird problems like this, pretty standard fare on AP test. And I think you can see why this is a tricky problem. If you just went from W to B, that would be the quickest, shortest amount of pipe, but it might cost more money. If you just went straight and over, you'd be laying a lot of pipe, so that's maybe not the best way to go. Okay, from A to B, they said was 8 miles. Okay, so the cost, got the water cost, land cost. So water cost is WP times $100,000. How far is it from W to P? A squared plus B squared equals C squared. And then $75,000 from P to B. Yeah. And it's only one variable, so that's nice. $100,000, x squared plus 36 to the 1/2. I would distribute that because the constant's going to go away when you take a derivative. C prime, set it equal to 0, go from there. But the hardest part is setting it up. Alright, worksheet 1, 8 through the end, 13. We'll go over some of those tomorrow. And if somebody will remind me, I'll show you a video of a calculus dog tomorrow. Calculus dog, don't let me forget.